Well, welcome back for the second talk this morning. We're going to hear from Rachael Boyd on diffeomorphisms of irreducible three manifolds.
It's okay.
Okay. Anyway, welcome to the second talk. We're going to hear from Rachael Boyd on diffeomorphisms of irreducible three manifolds.
Great. Thank you very much for the invitation. I'll finish at 10:36, so remind me if I don't. Okay, so yeah, thank you for the invitation. It's my first time at the Fields Institute and actually also my first time in Canada. So happy to receive your tourist recommendations. I've just spent, Feel free to say. I've actually just spent a month. I've spent a month in Montreal already, so I need to go home and water my plants. Right, okay, so this is based on this archive paper, and it's all joint work with Corey Bregman and Jan Steinerbrunner. We have some sort of follow-up work, which I'll talk about right at the end, which I will talk about right at the end. So that's my aim. Normally, I give this talk to either a geometric group theory audience or an algebraic topology audience. So this is both. So it will be a little bit different from maybe talks some of you have seen me or my collaborators give before, in that there will be maybe slightly less content, but it will be broader. So hopefully everyone will be happy. So M is going to be a three manifold. It will be additionally smooth, compact, oriented, does not need to be connected, can have boundary. We're interested in the diffeomorphism group of M. And so this is the diffeomorphism group, which is a topological group with the C-infinity topology. I completely forgot to say, I never knew Fred, but I have seen the work that his influence has had on algebraic topology, and I'm super excited to see more of it and hear more about him this week. So already, I was already very moved by the first story, and I'm very excited and happy to hear more about him as a person, as well as knowing about his work. Okay, so back to diffeomorphism groups. So we'll really be interested in BDiffM, which is the classifying space of diffM, or the moduli space. So one model for this is manifolds in R infinity, which abstractly look like M. So we call it the moduli space of M. So there's some abstract diffeomorphism from these manifolds to M. And this is a classifying space. What does it classify? It classifies smooth M bundles. So if we want to have, if we want to think about an M bundle up to diffeomorphism, these are in one-to-one correspondence with maps from our base space, which let's say is a CW complex, into BDiffM. And so in particular, we're going to be interested in the homotopy type of this classifying space. This is going to tell us many things. It's going to tell us about bundles over spheres. We might also be interested in characteristic classes of such bundles, in which case we would be want to compute the cohomology of this group. So when M has boundary, we'll write a partial down here, and this means that we will fix the boundary pointwise. So the diffeomorphisms will be the identity on the boundary. Okay, so that's the setup. We're interested in the homotopy groups. So these are BDiff is connected, and the homotopy groups are shifts of those of diff. So in particular, the fundamental group of this space is the mapping class group of the manifold. So these are diffeomorphisms up to isotopy, or the group of connected components. But warning, is that it's not necessarily a K pi 1 for the mapping class group. So in some cases it is, and I will tell you a bit about that in a moment. And then our theorems. So all numbered theorems are joint with Corey and Jan. Our theorems are, first of all, if our boundary is non-empty, then if we look at diffeomorphisms fixing the boundary, the classifying space is homotopy equivalent to a finite CW complex. So we call this homotopy finite for the rest of the talk. So we don't have an explicit CW complex. We can put a bound sometimes on the dimension when M is a connected sum of n hyperbolic manifolds. Then this is at most dimension 13n minus 7. But that's not very elucidating. So so yeah, it's more of a finiteness statement than anything else. And this very quickly gives us theorem B, which says for any M, so in particular for M closed, then we have that the classifying space is homotopy equivalent to a CW complex with finite P skeleton for all P. So another way of saying this, which we'll be more familiar with, is finite type, or for geometric group theorists, the geometric group theory analog is type F infinity. So we're not asking to be finite dimensional, but in each dimension we have a finite number of cells. Mm-hmm.
Are you using the fact that M is a 3 manifold? Have you used that yet?
To prove the theorems, we need to use that a lot. I will tell you about other dimensions on the next board. But okay, well, that's still true, that's still true, that's still true. And this is still true. Everything up to the theorems is true for all manifolds. Yeah. Okay, remarks. Any other questions? Oh, sorry. The question was, am I using the fact that M is a 3 manifold, which hopefully was clear from the answer. Oh, sorry. Yes. Yeah. M is a 3 manifold for the whole talk. That was the first line. Yeah. So the question was, I said for any M, I just meant that there's no conditions on the boundary. Yeah. So it could be M with boundary, it could be M closed. Yes. Okay. I see my wording was maybe a bit confusing. We're all on board now. Okay, great. So the first remark is that theorem A is appears as problem 3.48 on the Kirby problem list. I guess the 1997 version, which was version 2, and it's attributed to or said to be conjectured by Kontsevich. So we did the oriented case, so the non-orientable is still open. I can give some more comments later at why sort of the 3 manifold techniques we need are not quite up to scratch in that case. Most importantly, in 1997, also, Hatcher and McCullough proved the analog of theorem A for M irreducible. M irreducible means that every sphere in M bounds a ball. So in particular, pi2 is trivial. And just need to make sure I get my attributions all in. And another remark is in particular, theorem A implies homological finiteness. So the cohomology is finitely generated, finitely many degrees, which generalizes work of Narriman, who showed this with some slight conditions on what 3 manifolds we could have. And his paper first came out in the archive in 2021. It's been recently published. So now, let me tell you about other dimensions. So in dimension 2, analogs of theorems A and B are true for by work of Earl, Schatz, and Grumman for theorem A, and Earl Eels for theorem B. So this is that's for surfaces. And in dimension 4 or greater than or equal to 6, then the theorems are not always true. So in particular, Budney and Gabay more recently here, and Hatcher, Wagner, sort of more classically, showed that, so these are for sort of these dimensions respectively, they showed that the mapping class group of a specific manifold S1 cross the K minus 1, where the dimension is K, so this is the right dimension. So this mapping class group is infinitely generated. So that means you need an infinite number of, you need an infinite one skeleton, right, to build any BDiff. So neither of these theorems are true in general, but sometimes they're true. So in dimension greater than or equal to 6, and even if the fundamental group of M is finite, then the analog of theorem B holds. And this is by Bustamante, Kranick, and Coopers. So some partial results. There's also work of Baraglia and Kono if you'd like a different 4 manifold whose mapping class group is infinitely generated. And I'm sure there's others that I haven't cited. Okay, so that's the end of the remarks. Are there any questions? The rest of the talk, I'm planning to talk about the proof of theorem A. Okay. So the method of proof is as follows. So M is in particular reducible. So that means that it is not an irreducible manifold, right? So it means that it has a non-trivial prime decomposition, or it's an S1 cross S2. And so the first thing that we're going to try and do is cut our manifold up, and we're going to cut up using spheres because prime decomposition is done using connect sum along spheres into pieces that we know more about. Okay, so we're going to cut M along a disjoint union of spheres into irreducible pieces. So because we've cut along spheres, these irreducible pieces, they're not really irreducible. They all have some spherical boundary. So we unfortunately cannot use the Hatcher-McCulloch proof for irreducible manifolds. On that, in this irreducible case, the B-diff is actually a K-pi1. So it is actually a K-pi1 for the mapping class group, and they use very group theoretic techniques, therefore, to prove their finiteness. So even though it's a very inspirational paper to us, we couldn't actually import any of them when we were looking at the non-K-pi1 B-diffs. Okay, so we're going to then prove for the irreducible pieces minus some balls, which means that which is what we get after we cut along our spheres. And then we'll glue these finiteness results here together. Okay, so there's sort of multiple problems with this approach. Unfortunately. And so I will tell you some of the problems, and then I'll tell you how we fix one or two of them, depending on time. So problems, okay. So the first one is, we said we're going to cut along spheres. So this choice of spheres is by no way unique, okay? We're going to see exactly how non-unique it is. If we want to cut into irreducible pieces, for a start, we could choose different numbers of spheres, right? Also, if we choose sort of some set number sphere, there's infinitely many isotopy classes that we could choose. And each of those isotopy classes is not contractible. So there's a sort of a big hurdle there. So there's not a unique way to cut M into irreducibles. The Hatcher-McCulloch proof is not going to hold for the irreducibles once I've removed some balls. And the third problem, which I won't say more on actually, is this to do with gluing the pieces together. So if we know something about the diffeomorphism of a small manifold, and that small manifold appears as a piece of a big manifold, we don't necessarily know that that diffeomorphism appears as a piece of a diffeomorphism of the big one, right? So diffeomorphisms don't always extend over the whole manifold. And so we actually need to restrict to subgroups of diffeomorphisms which have the right mapping classes on the boundary. And that's a whole other thing, which unfortunately I won't get time to talk about, but it means that we had to introduce a new notion of homotopy finiteness, which we called hereditary finiteness, which takes into account the mapping class group on the boundary. Okay, so I'll just write diffeos of pieces don't necessarily extend to M. I'll point out where this comes up call this the gluing problem. Okay, so that's the sketch and the issues. Are there any questions? Okay, everything's crystal clear. Fantastic. Okay, so we're going to talk now about our choice of spheres. So decomposing three manifolds. So there's a prime decomposition for three manifolds. Where existence of this is due to Knaser and existence and uniqueness by Milner. So this says our three manifold M can be uniquely up to reordering decomposed as a connected sum of n manifolds which are irreducible, prime, but in particular irreducible. And then we only have one manifold which is not, so there's G copies of S1 cross S2. So this is prime and not irreducible. So our connected sum spheres, for a start, they're not unique. So they're not going to give us the unique way we wanted, but also they don't deal with these non-irreducible pieces that we also need to cut up. So we're going to define something a bit stronger. So sigma, so this is a disjoint union of spheres embedded inside M, is a separating system if M, this is my notation for if I'm going to cut my manifold along sigma. I can't just remove sigma because then what I end up with is not compact, but it's the interior of a, if you remove sigma, if you just imagine that you remove a little collar of each sphere, then you'll be fine. So this is M cut along sigma. So this needs to be is a disjoint union of irreducible manifolds minus some balls. And I will have to write this. On the next board. And a couple of conditions. We want no two spheres in sigma are isotopic. If they were, we would essentially just be cutting up we'd have an S2 cross I component when we cut up. And that would sort of ruin our finiteness. And each sphere in sigma is reducing. What that means is it reduces the number of prime components once we cut along it. So here's a schematic. So if I have say 2 irreducible pieces and 2 copies of S1 cross S2. I apologize if this is a super bad schematic, but this is how I'm going to draw it. Here's my P1 is going to be here. My P2 is going to be over here, and I'm going to draw my 2 copies of S1 cross S2 like genus. So in particular, here is an S2 around here. So we can now draw our spheres like curves on the surface. So here's an example of a separating system. So I need to cut up all my S1 plus S2 components, and I also need to make sure my, okay, so this is a fine separating system. So no two of my spheres are isotopic. And when I cut along these spheres, I end up with a P1 with 2 boundary components, a P2 with 1 boundary component, and some S3s with balls removed in the middle. Okay, so they're irreducible, so that's fine. Please, somebody let me know if they struggle with the colors. I brought my own colors to make sure that they were bright enough. Here's another example of a separating system, which would do just as good a job. These are supposed to be the same spheres. I'm just not drawing them exactly on top of each other. So this also is a smaller separating system. So it actually sits inside the red one. It's just got 3 spheres, and our pieces when we cut up just look like P1 and some boundary, and P2 and some boundary. So we define a space of these separating systems. So this is the set of all sigma, such that sigma is the separating system. And this is topologized as a subspace of the disjoint union over embeddings of spheres, K spheres in M. Actually, they're unparametrized embeddings. We don't worry about that too much. In particular, this blue and red separating system, they live in different connected components of this. And so we're trying to build some sort of space parametrizing the ways to cut up. And we'd really like to say, oh, it's unique up to homotopy, but at the moment it's not even connected. So we're going to do some magic on this to try and increase the connectivity. And actually, since we're proving finiteness, let me make just some notes. So first of all, there's a maximum number of spheres that can appear in a separating system. Because we don't allow isotopic spheres, you can't just keep adding spheres. So in particular, we could add, say, a sphere above. We could add a sphere up here. We could add a sphere over here. But then we would be adding isotopic spheres after that. There's also, if you look at the dual graph to a separating system, there's only a finite number of such graphs that can exist. And so we also use that. So there's sort of finiteness creeps in everywhere. And that's why we're sort of very particular with our definition. Because we have to put all of this finiteness together to prove theorem A. That's just two remarks on finiteness. So set M, this parametrizes the ways to cut up our spheres, and we'd like it to be ideally contractible. Okay, so we're going to endow set M with the structure of a topological poset. So this is just a space that also has a partial order in it. So we say that a separating system is less than another one if it's included inside. So in particular, the blue one is less than the red one in my picture. And then, oh dear, okay. And then we'll think about the nerve of that. We'll think about the nerve of this. So this has 0 simplices. I think maybe someone needs
Bizim
to mute.
öğrenci mi bu? Ne yardım ediyoruz?
Öğrencisi.
Onun
Zero
öğrenci
question?
değil. Galiba değil.
I'm going to mute them. Okay. So 0, I wouldn't like it if I was accidentally unmuted. They can unmute if they have a question. Okay, so
Acaba
if they have,
araba çalışmıyor ki nasıl?
She needs to mute.
she's left. She's left. Yeah, I muted her, but then she unmuted. Okay, never mind. Never mind. But let's go back to the 0 simplices. So this is our space of separating systems, and our p simplices are going to be given by chains in our poset. So in particular, this red and blue that were in different connected components, because they're related by the poset relation, now we're building a 1 simplex over them. And these are all spaces, and they're topologized as products as living inside here. And in particular, here's another finiteness thing. There can only be finitely many. These chains can only have finite length because these have a maximum number of spheres in them. So this nerve has finite height. Oh, okay, and so it's I can't reach there anymore. So it's a semi-simplicial space. So the face maps are going to be given by forgetting elements in our chain. Okay, so that's the nerve, and then the theorem is that if M is not S1 plus S2, then the geometric realization of this nerve, which actually just assigns an actual simplex to every chain there, this is contractible. So there are a few upshots to this. The main one for this paper is that this is sort of parameterizes the space of ways we can decompose M into irreducible pieces up to adding and removing spheres. And we've shown it's contractible. So this gives us our up to homotopy unique way of cutting up M. And the upshot, which I will star for later, is that we can model B diff M. This is the homotopy quotient of just a point over diff M. If you're not familiar with this, if you have a space and you want to take the homotopy quotient by a group, this is the same as taking the product with EG over G. It's also known the Borel construction. So this is just a fact, sort of by definition, but we can replace this with any contractible space with a diff M action. And so in particular, diff M acts on these spheres in our separating system. So we get a new model for our classifying space. And this model in particular allows us to compare diffeomorphisms of M with diffeomorphisms of pieces, irreducible pieces of M. So for this, so it allows us with some work to compare homotopy finiteness for BDiff with homotopy finiteness for BDiff fixing some choice of separating system. That actually means fixing setwise because our separating systems were unparameterized. Just fixing setwise. And so in particular, we're now just looking at diffeomorphisms which fix some chosen choice of spheres, and therefore we can restrict those diffeomorphisms to what's happening on the irreducible pieces. No, I didn't actually. So in particular, in the applications I'm going to talk about, this also holds. This is kind of a not necessarily needed here. Yeah. Yeah, it could be empty. So. Oh, sorry, I didn't repeat your question. Your question was, did I use the boundary was non-empty here? And the answer was no. What was your question? Yeah, so it's for some chosen sigma, yeah, for an arbitrary sigma we have to show. So for every sigma, yeah. Oh, did I not repeat the question? I'm so sorry. Okay, so the question, I just wanted to answer it. Oh no. Okay. So for the question was, do you have to show? Did by compare? Do I mean we reduce to showing that for every sigma, BDiff M fixing sigma setwise is homotopy finite? And the answer, which I gave, was that yeah, we have to show for an arbitrary choice of sigma. But the choice of sigma doesn't really matter in what follows. I mean, because we then just have to show for arbitrary irreducible minus poles. Okay, you want to do the mic instead? That might be better. I had every intention of repeating the questions. Any? I know. Are you guys okay?
You should believe that you're okay.
I am. Oh, sorry. They told me I was okay. I said I know. Okay. Okay. Great. Okay. So right. So this is this. So now this allows us to just think about irreducible manifolds minus balls, and the next theorem is that if M is closed and irreducible, and we have a ball in M, then BDiff fixing that ball of M is homotopy finite. So in particular, this is homotopy equivalent to BDiff fixing the boundary of M minus the interior of the ball. So this is, we just removed one ball, but you can do fiber sequence arguments, so removing one is enough. Okay, and let me say something about the proof. This is the geometric group theory portion. But no, there's a lot of geometric group theory influence here as well. I mean, this very much looks like the curve complex, especially the way I've drawn it. So first, we reduce to the geometric case. So there exists unique collection of JSJ tori such that, and this was proved by Hatcher, the diffeomorphism group of M fixing this collection of tori is equivalent to the diffeomorphism group of M. So all of the work that we had to do to reduce to this case, you don't need to do for passing from irreducible to geometric, because there is actually a unique isotopic. There's a unique isotopic class of JSJ tori. This was shown by I've completely forgotten the first J. Jacob, Scarlett, Shaylin, and Johansson, sorry, independently. That was a complete mind blank, sorry. So they showed that there's a unique collection of tori up to isotopy, and then Hatcher showed the isotopy class was contractible, right? So that means that this equivalence holds, apart from in one case where M is an Ossoff bundle over the circle, but we will not mind about that for now. And M cuts along these tori are either hyperbolic or Seifert fibered. So this reduces us to actually just the case of proving what we wanted to show for M, a hyperbolic or a Seifert fibered. Manifold. So we can suppose M is geometric, and now we have a fiber sequence argument. So this is true even when, well, this is actually true even when M isn't a 3 manifold. If you want to think about diffeomorphisms of M fixing a disk, I won't be able to write down the argument, but this is it's quite quick to show. This is homotopy equivalent to the orthogonal frame bundle of M, homotopy quotient in the action of diff. So this is basically because embeddings of disks are given by the frame bundle, which is then homotopy equivalent to the orthogonal frame bundle. And if you're geometric, then we can ask about isometries of the manifold. So if you're geometric and what's called a strong generalized Smale conjecture holds, so the Smale conjecture said that isometries of S3 into diff of S3 are equivalent, or diff S3 is O4. So the strong generalized Smale conjecture says that the isometries into diff is an equivalence. There's also a weak generalized Smale conjecture, which is just about the identity component. That is always true, but the strong one is not always true. But if this holds, then we can finish, because we can replace our the bottom group of our homotopy quotient with this homotopy equivalent group. And in fact, this acts freely on the frame bundle. So we have just a normal quotient, and this is a finite manifold quotiented by a Lie group, compact Lie group, and so it's homotopy finite. So this is homotopy finite. So that's good. The question is, when does this actually hold? I'm going to write like one sentence, and then I want to talk about the other applications in the last 5 minutes. So this holds e.g. for hyperbolic. So this is by Goodbye, Meyerhoff, and Thurston. And it also holds for elliptic manifolds. So this is by McCullough and Soma. And Bamler Kleiner. So this is very recent work. I saw an amazing talk by Bruce Kleiner at the Georgia Topology Conference. And we would never have managed to finish our theorem if this hadn't come out in, I think, 2022. So this is very fortuitous to us because we didn't actually realize we had to prove this at the time we started working on it. So yeah, so this holds for also non-Haken Seifert fibered manifolds. So this is by Hong, Kelly, Youngus, McCullough, and Rubenstein. This is an amazing book, mostly about Seifert fibered three manifolds and their diffeomorphisms. So yeah, there's lots of literature, and we're good in many, many cases. And we unfortunately have to prove for the Haken Seifert fibered case, which I don't know how many of you have worked with three manifolds, but there's an inordinate amount of cases when you work with three manifolds. And we have some nice flow charts in our paper sort of dealing with all of the cases, starting with these Haken Seifert fibered. And we have to prove the generalized Mayo conjecture for the Anasov bundles over S1, which didn't satisfy Hatcher's theorem over there. But okay, let's just say we've done that. And that's the sort of, there's also this gluing problem again, right? Because we have these geometric pieces and we want to glue them together to say something about the finiteness for the irreducible. But let me say something a little bit more about applications. Oh man. Shoot. That is not a flat surface for other speakers. Okay, so the first application is already out by the same authors. And just to tell you the kind of theorems that we can prove using this new model. So this is about B homeo and not B diff. And it is about four-dimensional handle bodies. So if you take the four-dimensional handle body of genus G, then its boundary is the three manifold given by G fold connected sum of S1 cross S2. And the theorem says that this map, which is given by restriction to the boundary, has a section. So I think this is nice because, well, in particular, it means that you can lift homotopy classes here up to here. So it's like a filling. You can extend your homeomorphisms. I mean, the pi naught version is you can extend your homeomorphisms, and then and this is now you can extend your homeomorphisms in families. So if you had a yeah, okay, let me just keep going so I can tell you the other. And the reason why this is homeo is because it uses the Alexander trick, which we don't have for diff. If we had it for diff, which I really hope we will do in the future, this would generalize a result of Loudenbach and Poinarou, which says that on the level of diff, on pi naught, you can always lift. So you can always fill mapping classes. And this is sort of used a lot by people studying for instance, Kirby diagrams of 4 manifolds. If you want to be able to say, I've drawn a Kirby diagram, now I can extend this to give me a 4 manifold, you have to use this result. But yeah, so this is just for homeo, and we have to use sort of topological versions of the separating systems. We have to use a 4-dimensional version, and we have to do everything with singular simplicial sets because we don't have the fiber sequences that we would normally have. So it's a bit of a different one. And then in upcoming work, oh no, okay. In upcoming work, I'll just write the theorem and then I'm done. We're also able to prove the cohomology, rational cohomology of the classifying space of 2 copies of S1 cross S2. We can compute it completely. It's given by this ring. Where these gamma generators have degree 4 and epsilon has degree 8. So I think this is very nice because it's a full rational, it's a full computation. G is 2, sorry, yeah. Thank you. G is 2 was the comment from the audience. Okay, I'm going to finish there. Thank you very much.